So today is going to be the last lecture of this series, and so far I've tried to, be very thorough with details. And today I don't plan to stick to that practice. There'll be a lot of hand waving. I mean, definitely towards the end of this lecture. So we'll start with, as usual, the recap. Last time we introduced this notion of S energy. So for a Borel measure mu, and S, we defined Is mu to be the integral and this can also be written as the convolution of the Rees kernel with mu integrated against the mu measure. So we saw that, okay, where the S growth condition. In other words, if we have a Grossman measure, so you've seen the proof of this lemma, right? And I have also stated that um, the converse of this lemma, I mean, essentially the converse of this lemma is also true. What I mean by that is that if the S energy of this measure is finite, then I can find a compact subset of the support of mu. And a measure nu, a new measure nu, which is compactly supported inside A with nu of A being positive. And this new measure satisfies the required ball condition. Okay. So we are not saying that if the measure mu satisfies the finite S energy condition, then mu will also satisfy the ball condition. That's not true. But we can say that you can find another measure nu, which is also compactly supported, and and its support is contained inside the support of mu, and this new measure nu will satisfy the ball condition, the S with the exponent S. Yeah. So how do I prove this? Let's take the finite S energy. Then I look at this integral, right? And we are saying that this integral is finite. So that means if I look at the inner integral, right, this inner integral must be finite for mu almost every y in Rd. And by pigeonholing, I should be able to say that there exists some constant m such that this set A, which is the collection of all y with the S potential, has positive mu measure. Yeah, that is mu of A is positive. Okay, so for this, I mean, I first use the fact that the S potential is going to be finite for almost every y in the support of mu, and then from there you have to use a pigeonholing argument to say that you can find a single m such for which the corresponding set A will have positive mu measure. And now I define nu to be simply the restriction of mu to, uh, to the set A. Okay. Um, and then you can verify all the required conditions in the I mean in the statement of the lemma. I mean in particular, mu of A is going to be positive, and if I'm looking at the ball condition, then this is actually okay. I'm going to write down r power minus s over there, and I can bound this integral from above by the S potential. I mean, obviously, for all y inside this ball, this quantity is going to be larger than r power minus s. And, uh, and this, by our assumption, is bounded above by m. So this is true for all x in the support of a okay. It's not so, I mean, it's actually pretty straightforward to see what would you do for other values of x as well. Okay. Um, I'll just leave that as an exercise, but I mean, this is the major part of it. Okay. So in view of lemma 1 and lemma 2, we can now, give an equivalent um, uh, characterization for the dimension of the Hausdorff dimension of a set. So let me just mention that complete exercise, check the ball condition for other values of x. So by combining lemma 1 and 2, we get this result that the dimension of this set is the supremum over all t such that I t mu I mean, sorry, such that there exists measure mu such that IT mu is finite. Okay. Um, to prove, I mean, to prove this proposition, we only have to, combine these two with perhaps the Frostman lemma, right? Because if I am looking at, suppose the dimension, suppose I choose a t that's smaller than the dimension of a, then by Frostman lemma, I know that you can find a measure mu that satisfies this condition with s replaced with t. Yeah. From there, I'll see that IT of mu will be finite. To go the other way, if IT of mu is finite, then you can use this lemma to say that you can find a measure mu supported inside the set A, satisfying the ball condition, and therefore, by the characterization of the dimension using the measures of of the required S growth, we have an equality here. Yeah. All right. So the next topic that so far we have looked at we have seen the Frostman condition. We have seen how the these measures satisfying the S growth is natural to sets of dimension S, and from there we have come to the single integral expression called the S energy expression. Now, I want you to see that, I mean, there is this very crucial analytical tool that we use in geometric machine theory, which is Fourier analysis, Fourier transform, something that I've not used yet. So, so that's what I want to discuss today. Okay, that we will introduce Fourier transforms, and we'll see how you can reformulate the energy integral using Fourier transforms. Yeah, and we'll see, I mean, what sort of immediate conclusions we can draw from this reformulation. Yeah, but before doing that, I would like to take a brief detour and introduce another class of problems called distance set problems. Yeah. Now, I want to do this because, I mean, of course, when Malabika is going to give lectures, I mean, she'll be talking about distance set problems. And this is perhaps the confluence point between this series of lectures with that of Malbika, and we will see that even in the case of the distance set uh, problem or the distance set conjecture, or in the investigation towards distance sets, the Fourier transform plays a crucial role. Okay, so we'll stop, you know, this discussion around energy integrals, or we'll pause the discussion around energy integrals here for now, and then we'll go to distance sets. Okay, we'll reach a point where where we will stop, and then we'll go to the introduction of Fourier transform, and I mean over there we'll see how these two, how Fourier transform can be applied in sort of investigating both ideas. Okay, right. So distance sets. The definition of a distance set is very simple. I just take a set in RD. The distance set represented as delta of A is defined to be the collection of all distances admitted by A. So that's the collection of all absolute values of x minus A, where x minus y, where x and y comes from A. Okay. Yes. So I mean, yeah, the norm. Yes. Now it's natural to sort of uh, think that when you have a large set, right, the set will also admit so many distances. So this is the the fundamentals. It's a very intuitive observation, or I mean intuitive, yeah, observation that you would make, and the distance set conjecture is is built on that, right? But it's an extremely difficult problem. Yeah. So before stating the distance set conjecture, let me just mention that by Steinhaus theorem, I hope the spelling is correct. Yeah. It's we know that the uh, if the set has positive Lebesgue measure, then the distance set, actually we know something more than that. We know that the difference set A minus A, in where I don't take the absolute value. So the difference set is, it's always going to be centered around the origin, right? Um, and this set will contains a ball centered around the origin. So in particular, I can say that the distance set will also contain, an interval amount of distances, with zero being the left-hand point of this interval, right? So this is in a way, sort of is aligning with this notion of large sets admitting large distances, right? I'm sorry, A minus A. A minus A is simply the collection of all x minus y. Yes. Um, but if the set has zero Lebesgue measure, then there is no need for A minus A for the distance set of A to contain an interval around the origin. Okay, we have actually, you can construct examples where this fails. Yeah, but distance set conjecture asks um, the conjecture tries to measure the size of the distance set using Lebesgue measure. So the distance set is going to be in the real line, right? So we ask if, or the conjecture states that if has Hausdorff dimension bigger than d by 2, then the L1 measure of the distance set must be positive. Okay. So here we have entered the realm of thin sets again, of sets of zero measure.
Now, I want to know what is this Steinhaus theorem? I mean, Steinhaus theorem statement is only that, is it?
Sorry?
Steinhaus theorem,
Yes, yes,
where
yes.
you're talking
Yeah,
about.
yeah.
That's the statement of it?
Yeah, yeah, yeah.
Okay, yeah, okay. Right.
So it actually comes as a consequence of Lebesgue density, theorem. Yeah. Okay. So this is the well-known distance set conjecture. It was posed by I'm sorry, I should put a crucial dimension restriction, yeah, which is that uh, d must be equal to d must be at least 2. So it is known that this conjecture fails when d equal to 1. You can construct sets of dimension. In R1 you can construct sets of dimensions close to 1, and still their distance set has zero Lebesgue measure. Okay. So the conjecture is therefore valid only in high dimensions. Um, it's stated in a very neat form, but as I said, it's an extremely difficult problem to solve. And there have been so many attempts at understanding or solving this conjecture.
So, in the case of D equal to 1,
Yes.
can the Cantor set be coming into picture somewhere? Is it? It's going to be the
So
distance set.
in the case of the Cantor set, right? So C minus C is actually going to be the entire, I mean, line segment minus 1 to 1.
Ah,
So it has positive L1 measure. So you don't want Quanta set. You need some other example. Yeah. Okay. Now, what are the non-results in this direction? Originally, I mean, the conjecture was proposed by Falkner, and he showed that if if dimension of the set is bigger than d plus 1 by 2, then the distance set will have positive Lebesgue measure. Okay. And Mattila and Jolin came, I mean, they gave a different result. They showed that if the set has dimension strictly bigger than d plus 1 by 2, then we can say more about the distance set. In particular, they showed that the distance set will have non-empty interior. Okay. Then people have looked at people have been improving this exponent quite a lot. Bourgain, for example, has shown this is for d equal to 2. I think he has also an improvement for higher values of d. So he showed that if the dimension of the set is bigger than 13 by 9, sorry, 13 by 9, then this holds. Then after him came Wolf. Again, in the plane case, he showed that if the dimension is bigger than 4 by 3, then this is true. Yeah. Finally, I mean, there are few other results as well, but in the plane at least, the best estimate, the best result we have so far is by this group with with the Larry Guth, and they have shown that in the plane. This is in the plane. If the dimension of the set is bigger than 5 by 4, then the distance set will have positive L1 measure. Okay. I mean, people have also tried to understand this problem from below, as in they have looked at, uh, they have tried to find a lower bound on the dimension of the descent set as well. So there are various types of results that's saying that if the dimension of the set is larger than a particular exponent, then the dimension of the descent set will also be larger than some other exponent. But so far, the conjecture is still unresolved. Yes.
I also wanted to know because you mentioned Mathilas and some of their, his co-authors.
Yes.
That. So they showed that, the interior is going to be non-empty.
That's right.
There's nothing in that direction.
People have considered generalizations of this problem. For example, the group of Iosovich, they've considered,
Alexisovich?
yes, they've considered chains.
Okay.
So instead of, I mean, so in the case of distances, you're only looking at the difference between 2 points, right?
Okay.
He looked at, he looked at whether I can find chains like say x1, x2, x3, where you prescribe the difference between x1 and x2 and x2 and x3. So they have a result where they have shown that I can find chains of lengths t1 and t2 coming from an interval. So that'll be a generalization of Mathila's result. Yeah, so that's yeah, and there are various other types of results as well. This is one thing that have come to my mind right now. Okay, any other questions? Is the problem clear? All right. I mean, sorry. Yeah, I should mention this. What? Of course, there is this result by Rani and Pramanik, right? Where they have actually. So Matilda says that if this set has dimension bigger than d plus 1 by 2, then the descent set will contain a non-empty. It will have non-empty interior. In particular, it will contain an interval. Now, in the paper of Rani and Pramanik, they have explicitly shown which interval it will contain, and the endpoints of this interval depends on the host of the dyadic host of content of the set A. But over there, they have assumed that the set A has a dimension so close to D.
Definitely much smaller than the d plus 1 by 2. Is that what
It
you're saying?
can be no, no. They are in their paper they are considering sets of dimensions so close to D, and
Uh-huh.
they have an additional assumption in terms of in terms of the dyadic host of content of the set. So they need the dyadic host of content of the set to be large. They need the dimension of the set to be large. Under these two assumptions, they could they could quantitatively find out what is the interval that's going to be contained inside the distance set. Yeah. Okay. So first of all, let me just show you where this exponent d by 2 is coming from. Okay, there must be a reason for why he has proposed d by 2 as a sharp exponent, right? So we have a sharp example here, or sharp examples. For any dimension, I mean d is bigger than or equal to 2, and for any dimension s between 0 and d by 2, there exists a compact set A in Rd with dimension of A is equal to S, and dimension of the distance set is at most 2S by D, which in particular is strictly smaller than 1. Yeah. Perhaps this is the only result for which I'm going to give a thorough proof today. The construction of this set, okay, is follows a candle-like construction. Yeah. And I mean, first of all, I mean, when you think about constructing a set that satisfies this condition, let's I mean, what type of set will you think of? You need to find a set A that has sufficiently large size, but it should not admit too many distances. In other words, I mean, it should have so many repeating distances. Yeah, it can have so many distances, but they should be repeating as well. Yeah, and this sort of forces us to look at constructions that are based on integer lattices. All right. So how do I construct this set? Let mk be a sequence of rapidly increasing natural numbers. Say k plus 1 is bigger than mk per k. Now define ak to be, maybe I can just write here. Ak to be the collection of all x in Rd with whose coordinates are x1 all the way up to xd, and each xi is yeah, for pj in I mean for some pj, some pi in 0 1 all the way up to mk, and for all I from 1 to d. So let's draw out this guy. Okay, and A is going to be the intersection of all these AKs. So let's try to draw this out. So when I want to draw AK, I mean, suppose I'm looking at D equal to 2. Then first of all, I want to, yeah, maybe instead of looking at all points in RD, I should be looking at all points inside the unit cube. So here I have the unit cube. I divide this guy into grids, where each length is 1 by mk. Yeah. And now what do I do? I consider, at every lattice point, you consider a rectangle, sorry, a square, whose side length is 2 times mk power minus d by s. Yeah. So it's the union of all these squares. Yeah, like that. In my notes, I have specifically said don't draw a lot of grids, and that's precisely what I've done here. So the side length of this guy is mk power minus d by s. Sorry, 2 times mk power minus d by s, which is, when mk is extremely large, you can see that this guy is actually much smaller than mk power minus 1. So these, squares are not intersecting with each other, all right? So this is my AK, and we have defined A to be the intersection of all these AKs. Now I want you to check. So see, we have seen similar constructions before, in the series of lectures. And I would like you to check whenever you get time that the dimension of this set, so verify that the dimension of this set is exactly equal to S. Yeah. And I mean, showing the upper bound is pretty straightforward here because I can see that each AK is covered by, I mean, these rectangles, right? And and what do I know about the number of these rectangles, these squares? How many squares are there? How many? I'm sorry? MK, how many rectangles, how many squares are there? Yeah, when D equal to 2. It's mk per d, right? So in RD, when I'm looking at AK, AK is a union of mk per d, many squares, and each of which has a side length of mk per minus d by s. Yeah. So so with that, you should be able to easily verify that the dimension of the set is bounded above by s. So you have a cover, you have specific information about the diameter of this cover, I mean, of every element in this cover. And you also know how many such sets are there in this cover. Okay, so using that, you should be able to easily find out the dimension of, you should be able to bound the dimension of A by from above by S. To obtain a lower bound, you remember we obtained this formula for the dimension of the product of two sets. The dimension of the product was bounded below by the sum of dimensions, right? So you use that formula iteratively and then see that see that I can reduce this whole scenario into d equal to 1. Yeah. And when d equal to 1, this construction is kind of similar to the generalized construction of Cantor sets that we looked at, maybe two lectures back. So you sort of draw parallels with how we argued over there, and then you show that you can also obtain a lower bound for the Hausdorff dimension of this set. Yeah. Anyway, so that's the um, yeah, that's an exercise for you. Now, when I look at delta of A, I mean, obviously it's actually contained inside the intersection of delta of AK, right? So let me try to pick a different distance t in delta of AK and see how I can relate t with the differences between the centers of these squares. Okay. Sorry.
What is
Oh, sorry. This is AK. Yeah. So let t be in delta of AK and say t is actually the difference between x and x prime. So since x and x prime lies inside AK, I can find two vectors p and p prime in AK. I'm sorry?
PD prime?
Yes. Such that x belongs to the square whose center is p by mk, and x prime belongs to the square whose center is p prime by mk. So it's that xi minus uh, pi by mk and xi prime minus pi prime by mk. They both are bounded above by mk power minus, it's d by s, isn't it? Yeah. And these are it's on the these p and p prime lies on the integer lattice, so it's an element of ak intersection zd. Yeah. Or uh, yeah, zd, that's right. Is that correct? No, that's not exactly correct because it's p by mk that lies inside. So I can write it as maybe mk times ak intersected with z. Anyway, I mean, the point being, p only takes the coordinates of p are integers. So because of this, condition or this inequality, I can check um, that the distance between p by mk minus p prime by mk minus t, which is nothing but p by mk minus p prime by mk minus x minus x prime, right? So this is, yeah, I mean, by triangle inequality, you can check that this is bounded above by, let's say, 4 times square root d times mk power minus d by s, right? Because I mean, I know that coordinate wise, xi's and pi by mk are mk power minus d by s apart. So the distance between the vector x and the vector p is at most square root of d times mk power minus d by s. Yeah. And say, I mean, similarly, you can estimate the difference between x prime and p prime by mk. So using that, I can show that this is bounded above by 4 times, say, square root of d times mk power minus d by s. Yeah, using this inequality. So yeah, so that means, if I mean, what does it say? Started with an arbitrary t in the distance set, right? And we are saying that you can capture this t inside an interval centered at p by mk minus p prime by mk, with a length of square root of d times mk power minus d by s. Yeah. So it follows that delta of ak can be covered by these intervals. Um, let's actually count how many such intervals are going to be there, right? See, p and p prime are at most mk. Yeah. So the values of p minus p prime is also, sorry, the coordinates of p and p prime are at most mk. So the absolute value of p is at most what, square root of square root d times mk, right? And so you can, I mean, I know that p minus p prime whole squared is going to be an integer all the time. Both p and p prime has integer coordinates. So maybe I can just mention that first. So since P and P prime are in ZD, and their size is bounded above by square root D times MK.
The notation is different and Z power D.
Oh yeah, sorry. Thank you. So so yeah, because of these conditions, P minus P prime squared is going to be an integer at most D times mk squared, or maybe four times D times mk squared. Yeah, I mean these constants don't really matter. Only the power of mk matters. Okay. And you see that's a drastic sort of reduction from how many intervals or how many squares you had in this collection. Yeah. So this is why we were sticking to like earlier, for example, in the case of that set in RD, we were covering the set by mk par d, many sets, many rectangles, and now in when I come to the distance set, I only have mk squared many intervals that are going to cover the distance set. So we can cover delta of ak with at most 4D mk squared many rectangles, sorry, many intervals of length that that would be 8 square root d mk power minus d by s, or 4 square root d mk power. Yeah. Then we can obtain the we can give an upper bound for the 2s by d dimension of the descent set. Okay. And this is going to be bounded above by lim of the uh, the s power of the diameter of these intervals. Let me call these intervals, say, I, K, K is fixed, I is the index. Then I have diameter of I, Ki to the power s. And this is to the power 2s by d, sorry. And this is bounded above by, so you can see what's happening here. The total number is of the order mk squared. The diameter of each interval is of the order mk power minus d by s. So when I take the 2s by d power of it, they just cancel out, and you get a uniform constant here. Yeah. So consequently, the 2s by d, consequently, the dimension of the distance set of A is at most 2s by d. Okay. So that's the example, that's a sharp example that you require for the distance conjecture. Any questions? All right. All right. So how do you study the distance problem? Okay. In most of the results, in fact, in most of the results that I've listed, uh, you'd see that they argue by first constructing a measure on the distance set. So if they look at a very specific measure called the distance measure, okay, that you are going to introduce on the distance set, and then you want to talk about properties of the distance set by investigating what sort of properties we can deduce on this measure, on the distance measure. Okay. So how do we study? So if the dimension of the set is bigger than S, then Grossman lemma gives me a measure mu that's compactly supported Borel measure with support contained inside a finite Borel measure with support contained inside A, and satisfying a ball condition, satisfying the S ball condition. I am also going to assume that this measure is a probability measure. Okay. Now, as I was saying, you construct a distance measure on the distance set. And how do I construct it? We look at the distance map, okay, say L from A cross A to the distance set of A, which maps xy to mod of x minus y. The distance measure is going to be, so you see that since mu is a probability measure on A, mu cross mu, the cross product of mu and mu will give me a probability measure on A cross A, and I just take the push forward of mu cross mu under this distance map. Okay. So we define the distance measure delta mu of I mean, as a push forward measure under this distance map. In particular, if B is a subset of the distance set, then delta mu of B is going to be the size of mu cross mu, sorry, the size of all the pairs x y such that their distance gives me an element in B. So you measure the size of this set in terms of mu cross mu. Yeah. Or I mean, equivalently, I can also uh, define the uh, to show the distance measure as phi of mod x minus y d mu of x d mu of y. This is true for B in the distance set of A, and this is for all test functions. Test functions phi from delta of A to R. Yeah. So it turns out um, you can give a sort of a neat expression for the distance measure using the spherical measure. Hmm. So let sigma t denotes the surface measure, the spherical measure supported on the the d-dimensional d minus one dimensional sphere of radius t in RD. Okay, so as it turns out, you can write down. So this is a very formal expression. It's not actually true, but for running, as I've said, since I'm going to sort of lose rigor in this part of the argument, I'm just going to tell you formally that the distance measure can be written in this fashion. Okay, so it turns out you can write down the distance measure as the convolution.
What do you mean by the spherical measure?
The natural measure you have on the, so you have, I mean, for when t equal to 1, you're familiar with uh, I mean the integration against the spherical coordinates, right?
That is
Yes.
okay.
So here I'm looking at a measure that's supported on the t dilated, the dilated sphere. Yeah.
Okay.
Yeah. So this is okay. I mean, formally, you can write down the distance measure as, I mean, in the form of a function here, as the convolution of sigma r with mu integrated against the mu measure. Okay. Now, this might be highly sort of non-trivial at the moment for you. I mean, there's no reason for you to consider, to even think that the distance measure should take this form. Okay. So just to motivate why it should be something of this form, let me just take, instead of the measure mu, let me just take the characteristic function of a set A, where A is of positive. Oh, I already used the notation A before. Let me choose a set B. Okay. So why is this true? Or the heuristics behind this formula. So consider the formula with mu replace with the characteristic function of a set B. Okay, and B is in fact a set of full measures. This is a thick set. So say the Lebesgue volume, the Lebesgue measure of B is positive. Yeah. If I look at, and let me also thicken the spherical measure here. Instead of sigma r, which is the measure supported on the R sphere, I'm going to thicken it by, say, epsilon, so that instead of looking at the sphere, I'm looking at annulus. Okay, an annulus of thickness epsilon, but around the sphere of radius r. Yeah. So if we consider this integral sigma r epsilon, which, as I said, should be thought of as the characteristic function of this annulus, okay, of thickness epsilon, send around the sphere of radius r. Convolution of that guy with the characteristic function of b, evaluated at y, integrated against the characteristic function of b again. Yeah. So this is the right hand side. Yeah. Now, what does this guy measure? Yeah. Yes.
Yeah. BV has got a question. Can you just see? So here, he's
Is a
written down.
question.
Yeah, there's a question to that. So,
You see, sigma r is a measure,
That's right.
mu is a measure, their convolution is a measure.
No, yes, yes.
What is y there?
That's see, as I've said, this is why I've given all the warnings here. This is a formal statement. This is not a rigorous statement. This is not like
Ah, ah,
mathematically
ah.
accurate.
Okay.
Yeah.
Hmm.
So to make it rigorous, I have to basically approximate mu with, I have to thicken mu and
Ah, okay.
and consider mu epsilons,
I see.
which
And
are
take that.
basically epsilon thickened mu's, and then you have to consider this integral for each of those mu's or each of those epsilons, and then you have to take the limit of it. That's,
Okay.
I mean, so that would be the rigorous version of it.
Ah, okay. Okay.
Since I didn't have the time to get into the details, I thought I'll just stick with this.
Yeah, that's fine.
Okay, yeah. Thank you for the question. So, yeah. So why is this true? I looked at this guy, and then I look at this convolution. Now, when is this convolution, or what is this convolution actually measuring, right? So this, by definition, is going to be uh, y minus x uh, d sigma t epsilon of x. So, so you can see that this is simply measuring the intersection between the volume of the intersection between B and this annulus. I'm sorry, I keep going back between these symbols. Yeah. So you can think of this expression as the volume of this set B intersected with this annulus, which is basically, as I said, is an epsilon thickened annulus centered at y with radius r. Yeah. So this should be B intersection y plus the epsilon neighborhood of r sphere. Yeah. So for each y, you are looking at how many, how many points x is going to be there uh, in B and also in this annulus, right? But what is the property of this annulus? I mean, if x lies in this annulus, then the difference between x and y is roughly r, right? It's actually, epsilon close to r. So, so this set is okay. However, B intersected with y plus the epsilon neighborhood of r s d minus 1 is simply the collection of all x in B such that uh, x minus y is epsilon close to r. Yeah. So for each y, this convolution, you have a question? Dhruv? Yeah. For each y, this convolution is measuring how many x is going to give me a distance that's epsilon close to r. Yeah, and then now you are again integrating against that with, the characteristic function of b of y dy. So now I also impose y to be in b. Yeah. So essentially, in total, I mean, this whole integral is telling me, I mean, is measuring the size of all those pairs x and y, such that their difference x minus y is epsilon close to r. Yeah. And now letting epsilon goes to 0, you see that, this integral essentially measures the size of this whole pairs xy such that their distance x minus y is exactly equal to r. Okay, so that's the motivation behind considering this integral. Yeah. Now, yeah. So from this formal expression, you can see that the distance set problem, or that has some sort of similar structure with the energy integral that we looked at, because over there you were considering an integral of I mean, of this form, but then sigma r was replaced with the Rees kernel over there, right? Um, so using Fourier transform, I mean, I don't have much time left anyway. So using Fourier transform, you can actually reformulate both these integrals, in both the energy integral and this integral into, I mean, an integral involving Fourier variables. And I mean, all these studies that I listed, they all consider this integral I mean, they study this integral using Fourier transforms. Okay.
So when
Yeah.
you use the Fourier transform, most probably, I mean, so how do you
I'm
really
just
make?
going to
Yeah,
I'm just going to say that, yes. Okay, so just to conclude here, therefore, the integral s- star, all right, now Fourier transforms. Um, are you familiar with Fourier transforms? Oh, you are, okay. I mean, I'm assuming you guys are already are, right? Great. So, so okay, that's great because then I don't have to list out all the properties of the Fourier transform. Yeah, let's just recall the definition of the Fourier transform. So for f in L1, uh, f hat of xi as e power minus 2 pi I x dot xi um, f of x dx. So apart from, you know like, I mean, you can verify these formulas very easily. So we know that whenever f and g are two nice functions, like say lying in they are Schwartz class functions, or maybe say smooth compactly supported functions, then this holds. We also know that this product formula holds f hat of x g of x should be same as f of x g hat of x. That's a product formula. And finally, we have the Parseval's identity, which says that f of x, the complex conjugate of g bar, uh, this is this is equal to uh, f hat times g hat, complex conjugate of that, and the integral of that. So this is the Parseval's identity. Some standard Fourier analysis. Okay. Now, I can extend the definition of Fourier transforms to measures as well. Um, and oh, sorry, I mean, I wanted to talk about the Rees kernel. So for Rees kernel, I mean, so this is true whenever uh, f and g are nice functions. Um, for the in the case of Rees kernel, I cannot directly use this formula to define the Fourier transform, obviously, because the Rees kernel is not integrable. It's not going to lie in any of the LP spaces either. Yeah, but over there you define the Fourier transform in a distributional sense. Yeah, so now okay, so Fourier transform uh, in distributional sense. What I mean by here is that um, for whenever g is a general function g of x, I mean I can define the Fourier transform of g uh, in this fashion. So the Fourier transform of g satisfies this identity, and so this is the product formula, right? Whenever g and g hat could make sense usually, but now I'm using the same formula to define a g hat even for those g's for which I cannot directly use this formula. Yeah. So in this sense, I can define the Fourier transform of the Rees kernel. Yeah. And with some work, you have a question? Yeah. With some work,
Perhaps it is better that you mention that G is a generalized
yes. Yeah, I intentionally did not write it write it down here because because then I'll have to explain what that is, right? Yeah. So I'm just going to say for general functions. Is that okay? We define g hat using the formula or using the identity. So g hat, yeah, g hat is this function that gives you this identity. Now, with some work, in this sense, you can show that the Fourier transform of the Rees kernel is some constant that depends on both S and the dimension of the ambient space times mod xi power minus d minus S. Okay. So if I take the energy integral, Is of mu, which was Ks convolved with mu integrated against mu. Now I can apply, so these are again formal calculations because you need some more justifications to how I can run these steps. Okay. But formally, I'm going to apply uh, Parseval's identity here, and that gives me the Fourier transform of this whole convolution mu hat its complex conjugate d xi. Yeah, so this is coming from Parseval, and then I know what is the Fourier transform of the convolution. That's simply the product of the Fourier transform of Ks and the Fourier transform of mu. But Fourier transform of mu hat and the complex conjugate of mu hat multiplied gives me the square, the absolute mod squared of mu hat. So that gives me that, and then I have the so these are all me just warning formal calculations, and this is giving me, from this formula, this is giving me some constant times mod mu hat squared times mod xi par minus d minus s d xi. Yeah. So you see that the energy integral can now be returned in the frequency variable in this particular form. Yeah. So as an immediate consequence, you can see that if mu has some sort of Fourier decay, for example, if mu hat of xi decays larger than mod xi par minus s by 2, then you can actually show that this integral converges. Okay, so the decay of the Fourier transform of the measure then can be used to show that the measure has finite S energy, and consequently you are able to show you are able to give a lower bound to the dimension of the support of the measure. Yeah. So that's one sort of immediate observation uh, of this reformulation. Okay, now without stating that, let me go back to our distance problem, right? Now over there, we had the energy, we had um, this integral, right? Where the convolution is now happening between mu and the spherical measure of the R sphere. Yeah. So for the distance problem, for the distance measure, delta mu of R, again by similar computations, I can show that it's actually equal to mu hat of xi squared, um, the Fourier transform of the dilated mu measure. So that will be dilated sigma measure. That will be sigma hat of R xi d xi. Okay. And then you are sort of trying to understand when this expression is going to be bounded. So which is what Falconer does. So Falconer shows that this integral is going to be bounded for, whenever, whenever the support of mu satisfies certain condition, in particular if it has Hausdorff dimension bigger than d plus 1 by 2, then I can make sure that this measure mu has um, finite S energy where S is exactly equal to d plus 1 by 2. So you use the fact, and you use also the observation that, this is well-known identity that gives you Fourier asymptotics for the Fourier for sigma hat. Yeah. And so combining these two observations, you will be able to show that this integral is uniformly bounded. Okay, sorry, it's bounded above by some constant, and that's, at the core of it, that's the observation that Falconer makes to show that the distance will have positive L1 measure. Okay, so yeah, I know that the last part has been sort of a mess, like a sort of hand waved a lot, but I think, I mean, since we don't have more time, I guess this is sort of a good place to stop. Yeah.
Perhaps give a reference where they can read it.
Oh, yes. So many. So many. So this whole relation between, Fourier analysis or Fourier transforms and Hausdorff dimension is uh, is detailed in this book called Fourier Analysis. And Host of Dimension by Matilda. There are a few other books that I've used throughout, most of the examples that we looked at in the first three lectures came from the geometry of fractal sets. Uh, by Falkner. And there is also, I think, few examples came from fractal geometry. There is a subheading, I forgot the subheading, but it's fractal geometry and then something, again by Falkner. Now, another book that has covered these topics in so much rigor. So fractal geometry is accessible for a broader audience. Things like the Frostman lemma is stated in a slightly different fashion over there. Okay, but if you want more rigor, then you either refer to either the geometry of fractal sets or um, okay, this I don't remember the name of the other book of Matilda. Yeah, geometry of sets and measures. In Euclidean space. This is also by Matilda. So it's either Matilda or Falkner. Right. Do you have any other questions? Okay, are there any questions online?
Yeah, just one question.
Yes.
You see, Hausdorff dimension does not depend on the metric, either Euclidean or L1, L infinity, right?
I'm sorry?
Hausdorff dimension,
Yeah.
whether you take Euclidean distance or L1 or L infinity, right? Supremum of the coordinate, because each is bounded by constant times the other.
Right.
Right? But however, the distance set, does that depend on the metric?
I mean, yes, right.
Yeah.
The definition.
So,
I mean, see, when you define the Hausdorff of dimension, we are taking the s power of the diameter. Over there, the metric will come into play.
correct. So it doesn't matter what metric you take, right? Usual Euclidean L1, L infinity, right? Summation mod xi or
Because they are comparable, you're saying.
because they are comparable. But the same may not apply for the distance set, right?
I guess so. I'm not, and
Yeah.
I guess so.
No,
Uh,
no, but the distances are also comparable, isn't it?
yeah, so they should
Why
be.
should
Why should
there be a difference? I didn't understand the question. Maybe.
Oh wait, are you? I mean, are they able to listen to you?
Yeah. Yeah.
So no. So Sundari is asking. I mean, why should they be different? Because the distances over there also must be comparable, right?
No, because distances, many of them may coincide, you see. Earlier, many distances are different in the Euclidean distance, but now many differences may be equal. Many distances. So you can't compare the Lebesgue methods, right?
Mm. No, I'm sorry. I can't actually quite picturize that. So
Yeah.
if
Anyway,
I
we can think about it. Yeah, yeah.
yeah. Um, okay, Professor, we can discuss that. I think we'll just
Yeah.
wrap up
Right,
this.
right. Yeah, we'll stop.
Yes. Yeah, but yeah, thanks. We can think about it. But so just some, concluding comments or thanks. I mean, thanks to Dr. Sundari for arranging this wonderful set of lectures. It has been sort of a great experience for me, and I would also like to express my gratitude to CMI for both the invitation and the warm hospitality they have provided here. Um, I mean, I hope you guys have also enjoyed during this series. If you have any questions, which you probably must have, I mean, you can either email me or, I mean, you can also refer to these textbooks. They fill a lot of gaps that I have created. Um, and even after that, if you have any questions, you can just email me. Okay. Um, yes, I think that'll be it. Is there anything that you would like to say?
Yes.
Yeah.
The
Thank
speaker, let's thank the speaker for wonderful lectures. And so this is his last lecture today. And the next two lectures are going to be by Professor Malavika Pramanik, and they will be only online.